And with that, we can head into today's main presentation, which we'll have from Eli Slenders. Thank you for joining us. Eli works at the Italian Institute of Technology in Genoa in Italy. He has a bachelor's degree from Hasselt University in Belgium and a master's degree from the KU Leuven. He did his PhD at Hasselt University in the biophysics group of Professor Amelot, and there he already worked on high-resolution imaging with resolution in coherent and incoherent optical imaging with two-photon excitation microscopy. In 2019, he joined the lab of Giuseppe Vici-Domini at the Molecular Microscopy and Spectroscopy Research Institute at the Italian Institute of Technology in Genoa. And since March 2021, Eli is a Marie Skłodowska-Curie Fellow at this same research group. He's now working on time-resolved, low-light dose single-molecule imaging with the SPAD array detectors, and that's what he'll be telling us about today, how these can be used to push the resolution limit. Eli, please take it away.
Okay, first of all, thank you very much for the very kind introduction. And thank you for giving me the opportunity to present here today. Some months ago, we published a paper on bioRxiv on this concept that we call ISM-FLUX, and it gained quite a bit of attention. So I'm really happy today that I can explain a bit in more detail what we think ISM-FLUX is, what the benefits and maybe also the limitations are compared to other microscopy techniques and so on. So I'm really happy that I can present this here today. This is an overview of the talk for today. I will start with a brief recap of conventional techniques like confocal laser scanning microscopy and image scanning microscopy. And then we'll move to single molecule localization microscopy with, of course, a lot of attention on ISM-FLUX. So let's first think about what conventional laser scanning microscopy is. In a conventional laser scanning microscope, you have a laser beam that a laser beam that you focus with the objective lens onto the sample, creating a diffraction limited spot on the sample. And then the molecules, the fluorophores in the sample will absorb the light and emit fluorescence, which has a different color. So you can spectrally separate the excitation from the emission with a dichroic beam splitter. And then you focus the light, letting it pass through a pinhole and then detect it with a single element detector. And so you scan the laser beam over the sample to create an image. And for each position of the laser beam, you measure with a single element detector the emitted light. Now, when you use a single element detector, then you integrate all the light that passes through the pinhole, regardless of its position, of the position of the photons in the image plane. So you lose spatial information by integrating all this signal with a single element detector. And that limits the resolution that you have with a conventional confocal microscope. And to solve this problem, you can do image scanning microscopy, which is a technique where you replace the single element detector with an array detector, a small array of maybe 5 by 5 or 7 by 7 pixels that you place in the image plane of the microscope. And typically it's about 1 to 1.4 array units in size. So what happens now is that you scan the sample, but for each position of the laser beam, you don't have a single intensity value anymore, but you have a micro image, a small micro image of your sample. And so at the end of the measurement, you have a 4-dimensional data set because you have 2 dimensions for the laser position and 2 dimensions for the position of the pixel in the camera. So this 4-dimensional data set, you can look at it as a sequence of micro image that you record in time. But you can also think of it as a 5 by 5 series of scanned images. Because if you have a 5 by 5 pixelated detector, then every pixel records an image of the sample when you scan. So in the end, you end up with 25 images. And these 25 images are very similar, but they're not identical to each other. You can see that they are slightly shifted in the X and Y directions with respect to each other, which is caused by the position of the different pixels in the image plane. You can see it very well when you measure the point spread function of all the 25 pixels, what you see here. If we ignore a little bit the different shape here of the pixels near the corner, then you see that all the pixels have a very similar Gaussian shaped point spread function, but their position in the image plane is slightly different. And this is caused by the different position of the pixels in in the image plane. So you have these 25 images that are slightly shifted with respect to each other. Here you can see also an animation of the different point spread functions. And so these 25 images, you have to combine them somehow to create one super resolved image. And what you typically do is very simple. It's the pixel reassignment process, where you simply undo the shifts that you observe. And then you end up with 25 images that are all very similar. And then you can simply sum them all up to obtain one super resolved image. Here you see an example of the effect of ISM on a real sample of tubulin. On the left, you see the confocal image with a closed pinhole. So if you close the pinhole to, let's say, 0.2 array units, then you have a good resolution, but a low signal to noise ratio. And the reason is, of course, that if you close the pinhole, then you block a lot of light. So you have very few photons entering the detector. And then you end up with an image that it has a good resolution, but it has a very low signal to noise ratio. On the other hand, if you open the pinhole to about 1 to 1.4 array units, which is what you typically do in a confocal microscope, then more light will pass through it. So we will have a much better signal to noise ratio, but at the cost of worse spatial resolution. In ISM, you have the best of both worlds. You have a good signal to noise ratio and a good resolution. And the reason is that you have a good signal to noise ratio because the detector, the total size of the detector is about 1.4 array units. So you collect the same amount of photons as with a conventional confocal microscope. But since each pixel is very small, each pixel acts as an almost closed pinhole. So every image that you obtain has this super resolution or super resolved resolution in the image. So then when you sum up all the 25 images, you end up with one image that has both a good signal to noise ratio and a good resolution. The detectors that we typically use in our lab are spot array detectors, which are a small array of 5 by 5 or 7 by 7 pixels. And each pixel is a single photon avalanche diode. And all these spots, all these single photon avalanche diodes, act independently from each other. So whenever a photon hits one of these pixels, it will produce, let's say, a logical high voltage that you can then detect with an FPGA, for example. But all these pixels operate independently from each other. So it's not like you have a frame rate as you do with a normal camera. So with this detector, you have sub-diffraction spatial sampling of all the photons. And on top of that, you have still the temporal information of the arrival times of the photon with about 100 picoseconds precision. So this detector allows you to, for example, combine it with with photon time tagging to get, for example, the fluorescence lifetime. Here you see an example of the photon detection efficiency as a function of the wavelength for some typical spot array detectors. I will not go into detail, but I just want to show that typically for wavelengths around 500 nanometer, you have the maximum photon detection efficiency, and then it goes down for longer wavelengths. So when you think of using this detector in the context of single molecule imaging, very often you use fluorophores that emit more in the longer wavelengths, where the efficiency of the detector is not the best, but I will show later that it's possible to do. Another parameter that is important is the dark count rate, and this is a property of the detector that it counts, or you see counts also when there is no light. And typically this dark count rate is in the order of 100 to 1000 dark counts per second. For normal imaging, for normal ISM, this is not a problem because the count rate of the signal is typically a lot higher. But again, when it comes to single molecule imaging, typically the count rates are a lot lower. And then this is an effect that you have to consider. Spot array detection is a well-established technology now. It has been used for conventional image scanning microscopy, but also the combination with lifetime has been shown. Also a 2-photon excitation ISM, the combination with STAT, quantum ISM, SOFI ISM, and also for measuring dynamics, the combination of spot array detectors with fluorescence fluctuation spectroscopy has been published. So there are many applications already, not just by our group, but also by other groups. And so that raises the question then, can you use this detector also for single molecule imaging? And if so, what would be the benefits of this detector and what would be the limitations? So to understand this, let's look first at what is already out there. Which techniques are there already for single molecule localization microscopy? There are many different techniques, but I think in general, we can divide all the techniques into two classes. On the one hand, we have the class where there is wide field illumination combined with structured detection, like in the classical palm or storm or paint. In these techniques, you have always a subset of fluorophores that is active, that are spatially separated, ideally. And you illuminate the sample with homogeneous illumination, and you detect the emission with a large camera. So what you see on the camera then are these point spread functions, which you then analyze to find the position of the molecules. So what you can do, for example, is fitting a Gaussian through these point spread functions and then check where the center of this Gaussian is. And then you have, with sub-diffraction resolution, the position of the fluorophore. And you can repeat this process over and over again until you have found the position of a large number of fluorophores, so that you can have an image with a very good resolution. This technique is well established, works very well, and the localization precision that you have is given by sigma 0 divided by the square root of n, where sigma 0 is the standard deviation of the emission PSF and n is the total number of photons. So theoretically speaking, you can have unlimited resolution. Of course, in reality, the resolution is limited by the limited number of photons that you have. Some other limitations of this technique, I would say, are that you don't encode any spatial information on the illumination side because you illuminate homogeneously, which limits the resolution further. And also large cameras like EMCCDs, for example, they don't allow single photon time tagging. So the combination with the fluorescence lifetime measurement is very difficult. So this is one class of single molecule localization techniques. On the other hand, you have the class where you have structured illumination combined with single point detection. And I think the main technique here is ISM-FLUX, where you have a donut-shaped laser beam that you move around in what they call a targeted coordinate pattern. So you have the donut beam that you move, for example, to these 3 positions on a circle, as well as 1 position in the center of the circle. And then you measure the response of the fluorophore. So you measure the total count rate, or the total number of counts emitted by the fluorophore for each of these 4 positions of the donut beam. And then you can calculate in post-processing the most likely position of the fluorophore given the 4 counts that you detected. And you can do this in an iterative procedure where you start with a relatively large circle for the TCP, so it can be more than 100 nanometers, for example. And then in every iteration, you can decrease the size of this TCP so that you can basically zoom in on the fluorophore and get a better localization precision. There are several variations on this concept. For example, there is the technique pulsed ISM-FLUX, where you do a very similar thing. You have a donut-shaped laser beam that you move to these 4 positions, 3 on a circle, 1 in the center of the circle. And if you do it with a pulse laser, like they do here in pulsed ISM-FLUX, then you can combine it with the fluorescence lifetime measurement. One of the limitations of this technique, at least the way it was implemented here in this manuscript, is that you cannot iteratively update the diameter of the TCP over more iterations like you do here. So the localization precision is typically a little bit worse here compared to normal ISM-FLUX. Then another example is Rasterman, where again you have a donut-shaped laser beam that you move around in the raster pattern. And the advantage of this is that you can combine it with a conventional confocal microscope, where you also have this raster scanning. The only thing is that you need to have a donut-shaped beam, so you need to add the faceplate, for example, in the excitation. But other than that, you scan, just like with a confocal microscope, the donut beam around a single active fluorophore, and then again you calculate in post-processing the most likely position of the fluorophore given the observed count rates for each position of the raster. And then another technique is confocal single molecule localization microscopy, where you work with a normal confocal microscope. So you have a Gaussian-shaped laser beam that you scan very quickly over a large field of view. And then you get images that look very similar, like conventional storm or palm. But because you scan, you can use a single element detector with a very high temporal resolution. And so you can combine this technique with lifetime measurements. So all of these techniques have been developed and work very nicely, but of course they all have some limitations. Of course, for example, in the case of ISM-FLUX, you need a precise pre-localization step to be sure that the molecule is within the TCP circle. Because if it's not in the TCP circle, as I will show later, then it becomes very difficult for this approach to localize the molecule. So you need an extra pre-localization step, which takes a bit of time and photon budget, of course. Typically, these techniques also are limited to one molecule at a time. You can localize only one molecule at a time. And in the case of the fourth method, the spatial resolution is limited in the very same way as with conventional wide field storm or palm. It's good. It's definitely some diffraction, but it's not as good as, for example, ISM-FLUX. So then the idea that came to our mind is, what if we combine the two? What if we combine structured illumination, like you do here, with structured detection? And that is what we call ISM-FLUX. So ISM-FLUX is a concept more than just a single technique, a concept where you combine structured illumination. This can be a donut-shaped beam or a Gaussian-shaped beam or anything else, with structured detection by using a camera, by using a pixelated detector. All these techniques we call ISM-FLUX, and to distinguish them, we use a small letter P, R, or C for the specific methods. I have to say that the combination of structured illumination and structured detection has already been done before. Here are some examples. But in all these examples, you use the striped illumination pattern, the sinusoidal striped illumination pattern that you use in conventional structured illumination microscopy, and you combine that with large EMCCD cameras. So although you have here also the combination of structured illumination with structured detection, because you have these large cameras, you cannot combine it, for example, with fluorescence lifetime measurements, because these cameras have a limited frame rate and a limited temporal resolution also. And there is also readout noise, which, for example, spot array detectors do not have. So the concept of ISM-FLUX, what is it? In detail, you have a laser beam, excitation laser beam, that you shape into a donut shape or something else, and that you move to different positions in the sample. For example, in this case, we have 3 positions on a circle and 1 position in the center of the circle. And then in your sample, you have one fluorophore that is active, so that absorbs the laser light and that will emit fluorescence, and you detect the fluorescence with a detector array, for example, a 5x5 element spot array detector. Then what you observe is, for each position of the donut beam, you have a micro image like here. So you have in total 4 micro images in this case. And then you analyze these to find the position of the fluorophore. And to have an idea about how you analyze this, let's go back first to conventional ISM-FLUX. In conventional ISM-FLUX, you have a very similar setup, but in this case, instead of an array detector, you just have a point detector that integrates all the light that comes from the fluorophore. So for example, in this case, if the fluorophore is here and the donut beam is centered around this position, it will absorb a bit of laser light and you will observe maybe 29 photons. Then you move the laser beam to this position where the excitation will be stronger, and so the emission will be stronger. So for example, you have 45 photons. Then for the third position, for example, 13, and for the fourth position, 30 photons. So after the measurement, you have these 4 numbers. And then what you usually do in ISM-FLUX is you calculate what is called the maximum likelihood. So what you do is you use this formula, which tells you how likely it is that the molecule is at position RE, given the n photon counts that you observe. And you can calculate this for all the potential positions of RE, and then you check which one is the most likely, and that is then the position of the fluorophore. To do that, you need capital N, which is the total number of photons that you observe, the small n, which is the number of photons that you observe for each of the positions of the donut beam, k, which is 4, because you have 4 positions of the donut beam here, and pi, which is the probability that a photon is detected, let's say, by donut beam I. So this pi contains information on the position of the donut and also on the signal to background ratio. So what this is actually simply a multinomial distribution, so a generalization of a binomial distribution. But the idea is that you calculate the likelihood for all the potential positions Re, and you check where the likelihood is maximal. And this approach, the very same approach, can be applied to ISM-FLUX. In this case, of course, you don't have 4 numbers, but you have 4 times 25 numbers, because for each position of the donut beam, you have a micro image with 25 pixels. So it means that n, in this case, can be represented by a matrix with 4 rows, where each row represents one of the positions of the donut, and 25 columns, where each column represents one of the pixels of the array detector. So we have a 4 times 25 matrix. And also pi is now pij, which is the probability that a photon is detected by a specific combination of a donut and a pixel in the detector. So it contains information both on the excitation pattern and the detection point spread function of that specific pixel. Apart from that, the idea is the same. So you calculate this likelihood for all the possible positions in the field of view, and then you check where the likelihood is maximal, and that is then the most likely position of the fluorophore. This is an example. So let's say that the fluorophore is very close to the optical axis, and you have these 4 positions of the donut beams. Then if you do conventional MinFlux, so with a single element detector, you end up with a likelihood map like this, for 100 photons detected in total, and for ISM-FLUX, a likelihood map like this. When you zoom in, you will see that both are actually very similar. So you have a very well-defined peak, a single local maximum, that is very close to the actual position of the fluorophore. This is true both for detection with a single element detector and with an array detector. You may say that here with an array detector, it's slightly sharper, which is true, but in both cases, the maximum is very close to the actual position of the fluorophore. So both techniques work very well. But this is for a fluorophore that is within the TCP. If you move the fluorophore to some position outside of the TCP, you get a completely different picture. In this case, when you have a single element detector, the likelihood map is very different. Now you have a very broad distribution here with multiple local maxima, and also here, very far away from the actual position of the fluorophore, you have a high likelihood that the molecule is there, according to the data that you have with a single element detector. On the other hand, if you have an array detector, then you see that the likelihood still shows a very narrow distribution with a single local maximum very close to the actual position of the molecule. So this is an important advantage of ISM-FLUX because it allows you to localize molecules also when they are outside of the TCP circle. So you don't need a very precise pre-localization procedure as you do in conventional MinFlux. Let's say now that the molecule is not just outside of the circle, but very far away from the circle. Are you then still able to localize it? The answer is yes. If we look at the likelihood maps here, then you see that in all cases, wherever the fluorophore is within the field of view of the detector, we have a single local maximum very close to the actual position of the fluorophore. Of course, the limitation is the photon counts. If you have a molecule that is here very far away from the donuts, it will not be excited a lot anymore, and so then you will not observe a lot of photons anymore. But if you have 100 photons, then you can localize it over the whole field of view with very good precision. To make this more quantitative, we calculated the Cramer-Rao bound, which gives an estimate of the localization precision, of the best obtainable localization precision. And we calculated this analytically under some assumptions. And then you end up with this formula. So the localization precision is equal to L divided by 2 times the square root of 2n, with L the diameter of the TCP, so maybe 100 nanometers or 50 nanometers, and N the total number of photons. This formula is the same one as for conventional min-flux, but this is under the assumption that the molecule is in the center of the TCP. But as I said before, one of the strengths of ISM-FLUX is that you can also localize molecules when they're not close to the center or when they're even outside of the TCP. And that's what you can see here. These are some heat maps where you see the Cramer-Rao bound, so the localization precision as a function of the position of the fluorophore. If we take, for example, a diameter of 150 nanometers as an example for the TCP, then you see that very close to the center, we have a localization precision far below 10 nanometers, both for a single element detector and for an array detector. But for molecules that are farther away from the optical axis or farther away from the center, the localization precision becomes worse and becomes worse quite a lot for a single element detector, while for an array detector, it remains pretty stable. It worsens a little bit, but it remains pretty stable. And we can see this better when we zoom out, which is what you see on the right. Then you see that for almost the whole field of view of the detector, you have a very good localization precision. Very close to the edges, this is not true anymore. But again, this is because you don't have a lot of excitation anymore there. So if you don't have a lot of photons, then of course you cannot localize it properly. Here you see the same in a line plot. On the vertical axis, you see the average precision at a given position as a function of the position. 0 means the center of the TCP. And then as we move towards the right, we are looking at positions farther away from the center. And we see that for min-flux and for ISM-FLUX, we have a very similar localization precision near the center of the TCP. But then as the molecule moves towards, moves outwards, then for min-flux, at some point it increases very quickly, while for ISM-FLUX, the localization precision remains stable over a very large field of view, and only like around 600 or 800 nanometers, it starts to increase a lot. And again, this is mainly because you don't have a lot of photons anymore here. We have 90% of the excitation to the left of this line, and only 10% of the excitation happens to the right of this line. So of course, if you don't have a lot of excitation anymore, then you will not have a lot of photons, and then you cannot have a good localization precision if the molecule is here. But so we can conclude that if you have excitation, if you have emission, then you can localize it wherever it is in the field of view of the detector. Okay, this is one important key aspect of ISM-FLUX. Another one is multiplexing. Let's assume that we observe something like this. Then the question is, can we say for sure that there is more than one fluorophore active? And if there is, can we localize them? In other words, can we localize multiple molecules simultaneously? Because, for example, let's say that you have these micro images for the 4 positions of the donut beams. Then you may think that there are 2, because you see like a peak here and like another peak here. So you may think there are 2 fluorophores at these 2 positions. But can we be sure of this? And if we know that there are 2, can we localize them both simultaneously? So these are two questions. The second question, to localize them, if you know how many there are, is actually the easiest question. So let's say that you have 2 fluorophores, and you know that there are 2 fluorophores. To localize them together, you can simply expand the likelihood approach to more dimensions. So normally you have the likelihood as a function of RE, which is the position of the emitter. If you have multiple fluorophores, you can simply write the equation for the likelihood for multiple emitters. So this becomes a two-dimensional function for one emitter, a 4-dimensional function for 2 emitters, and so on. The only complexity that this gives you is that because you have a high dimensional space of the likelihood, you cannot calculate the likelihood in a map like I showed before, but you have to use an iterative optimization algorithm for computational reasons. But the approach is the same. You just calculate the position for the 2 or 3 molecules where the likelihood is maximal. But then you have to know how many there are. And to know that is more tricky. We came up with the following solution. So let's take a look, for example, at this simplified situation. Let's say that you have only one donor beam, only one position, and so you observe only one micro image, for example, this micro image. Then you may think, okay, there are two molecules here. I can already tell you in advance that the ground truth here is 3 molecules at the positions of the yellow stars. But the question is, how can we be sure that there are 3? And to do that, to answer that question, what we do is we first assume that there is just one molecule active, and then we localize it with the likelihood approach. And that gives us the result, for example, like you see here. So the likelihood will say that the molecule is in the position of the orange star, which is in between the 3 positions of the ground truth. And then you can calculate the micro image that you would have, theoretically speaking, if the molecule was there. And that gives this fingerprint image, this micro image, which you can then compare with the actual one that you observe. And you see already here that these are quite different. So this is most likely not the right solution. Then you can repeat the same, but assuming that there are 2 molecules. In this case, probably one of the molecules that you find will be very close to the actual position of the molecule. And the other position that you find will most likely be in between the other 2. Then you can again calculate the micro image that you would observe given these 2 positions. And then you repeat the same with 3 molecules. And in this case, you will end up with 3 positions very close to the actual position of the 3 molecules. So then you have these 3 micro images, and then you can simply compare the 3 with the one that you observed. One way to do that is by looking at the sum of the square differences of the pixel values and check where this has the highest similarity. And that is then the most likely situation. So both in terms of the number and the positions that you find. This approach works very well. We tested it up to 3 fluorophores at the same time, and it predicts correctly in more than 80% of the cases the number of molecules. So if you have 1 molecule, the algorithm says there's only 1. If you have 2, it says there's only 2, and if you have 3, it says that there are 3. In more than 80% of the cases. And the localization precision is also very good. For 2 molecules, we have an average of
It seems we have some connection issues.
can you hear?
Sorry, your connection just dropped off. I think, yes, you were saying the localization precision. That's when you cut out.
Okay, can you hear me now?
Yes, now it seems to be fine again.
Okay, did I already explain this figure on the left? Okay.
That part we still heard. Yeah, that graph was when we stopped.
This graph, okay, I will briefly explain this one again then.
Thank you.
So if we have 2 molecules, then we have a localization precision of about 12 nanometers on average for both molecules in more than 50% of the cases. For realistic parameters, I want to say, so for about 170 photons per molecule and a signal to background ratio of 3.5. So this is something that we were very happy about. So to come back to the question that I start from, let's say that we observe these 4 micro images, then how many fluorophores are there in the end? We thought intuitively that there are 2. What does the algorithm say? It also says that there are 2. This is the likelihood map. So you see the 2 positions here, and this is actually very close to the ground truth where we started from. So this algorithm, this approach works very well, and so we wanted to test it also on experimental data. And to do that, we used a simplified setup where we have 1 Gaussian beam, in this case, focused at a fixed position in the sample. And the sample here was fixed fluorescent beads on a slide, which we used just because they are very bright, and so they produce a lot of photons. And then when we apply this algorithm, we found these 2 positions. So the algorithm said that there are 2 molecules, or 2 beads in this case, and that these are the 2 positions. And it could localize them with a very good precision. But of course, we had a very high number of photons. And then we went one step further. We moved the stage 50 nanometers in the Y direction, so that we moved the sample 50 nanometers. And then you observe this micro image. And then we applied the very same algorithm again. And again, it said that there are two particles and their position is also shifted by about 47 nanometers. So just to show that the algorithm works very well. So this is a second key advantage of having this extra spatial information with the array detector. You can do multiplexing, which we tested up to 3 particles with simulations and 2 particles with experiments. So then the question is, if you want to implement this ISM-FLUX technique, which detector should I use? And there are certain parameters that you have to take into account, like the photon detection probability and the dark count rate. In the case of spot array detectors, there is no readout noise, and the temporal resolution is very good, so you can combine it with time tagging. But the photon detection probability and the dark count rate are still a little bit a limiting factor, let's say. What you see here on this graph is the average precision of so the Cramer-Rao bound as a function of the position. So again, 0 means that the fluorophore is very close to the center of the targeted coordinate pattern. And then as we move to the right, we are looking at positions farther away from the center. And this graph is the Cramer-Rao bound for realistic parameters of the detectors that are typically used in MINFLUX and in ISM-FLUX, so a spot array detector here. And then you see that if the molecule is close to the optical axis, close to the center of the TCP, then MINFLUX performs significantly better than ISM-FLUX because of the better specifications of single element detectors compared to array detectors. But one of the advantages, as I said before, is that you have a very stable localization precision over a large field of view, while for a single element detector, the localization precision gets worse very quickly when the molecule is not close to the center. Another detector that you could think of is, for example, a quantum CMOS detector, which has basically 0 noise and a very high photon detection probability. So in this case, the localization precision is even better, but the temporal resolution of these detectors are not good enough to combine them.
Lost you again.
Yeah, the connection seems to be breaking up.
Yeah, again.
Yeah, sorry, yeah, we lost you again, but it was only you were on the last on the previous figure, so
okay.
we only cut out for a few seconds.
Okay, I will continue. I'm sorry for the bad connection. What you see in the graph on the right is the ratio of the Cramer-Rao bound between an array detector and a single element detector. And on the horizontal axis, we have different dark count rates. Again, the ratio for an array detector compared to a single element detector. And on the vertical axis, the ratio of the photon detection probability of an array detector over a single element detector. So for example, the data point 1,1 shows the ratio of the Cramer-Rao bound that you have with an array detector over a single element detector under the assumption that the array detector performs equally as a single element detector in terms of dark count and photon detection probability. And if this is the case, which is of course an ideal situation, then the Cramer-Rao bound is about 0.5 times lower, so 2 times lower than with a single element detector. So ISM-FLUX performs twice as good as MINFLUX under the assumption that you can find an array detector with the same specifications as a single element detector. The current generation of array detectors or spot array detectors is not that good yet, but I want to emphasize that this field of developing spot array detectors is moving very rapidly, and for sure, very soon we will be able to cross the line towards the green region where array detection performs better than single element detection. So this stems us very optimistic. But okay, I still want to show experimental data as well, because we have spot array detectors already now that are very good. And so we wanted to test ISM-FLUX also on experimental data. So what we did was we implemented maybe the easiest of the ISM-FLUX approaches, which is the last one, the Confocal ISM-FLUX, where you have a Gaussian beam that you scan very quickly over the sample and you detect the emission with an array detector, and then you analyze the data. We did this for a DNA paint sample that you can see here. On the left, the video of the measurement, and on the right, the photon count rate as a function of time. So the DNA paint sample that we had was consistent of rods of 3 positions on each rod that are about 40 nanometers apart. You see that you have about 50 kilohertz of background. These are not dark counts, or not only dark counts, but mainly caused by freely diffusing fluorophores. But then you can still clearly see the peaks whenever there is a fluorophore that is stuck to the DNA origami. So we analyzed this in 2 ways. First, what we did was we just considered the signal of all the 25 pixels as if it was one big detector. So we just considered the sum of all the pixels, and we localized them like you do in conventional localization microscopy by fitting Gaussians through the observed particles. And then this is the result. So you see these localizations that are a bit scattered around. They are a little bit in groups, but definitely not what we expected. But this is without using the spatial information that we have with an array detector. Because we have now this array detector, we can use the spatial information to improve the localization precision. And the way we did this here was by applying the ISM reconstruction algorithm to every frame of the data set. So on the left, you see the sum of the 25 elements, and on the right, the ISM reconstruction of the same frame. And you can see that the fluorophore is more confined in space, which is expected because the localization precision for conventional localization with a camera is sigma divided by square root of n, as I said before, and the sigma is divided by square root of 2 in the case of ISM. So you have a square root of 2 times better localization precision. So then we did the same, we applied the same algorithm to the reconstructed video, and then we end up with this result. So on the left, you see the reconstruction for some 5x5, and on the right for the ISM-FLUX. And in this case, you do see indeed the 3 data points that are close together at the right distances. So this indicates the importance of having this spatial information with the array detector. But that's not everything, because also you have a very good temporal resolution with array detector. So we decided to combine this measurement of DNA paint with measuring the fluorescence lifetime. And this is not so straightforward, because we have now a 5x5 array detector. So it means we have 25 pixels, 25 channels, or in the case of a 7x7 detector, 49 channels. And so to do lifetime, you need to have a system, a time tagging system that has so many channels. And right now there is no commercial system that can do that. So we developed what we call the Bright Eyes TTM, which is a time tagging module for single photon microscopy, which is also open source. So if you want to build it yourself, you can find all the information online, both the hardware and the software components. And so what you can do is you can connect every pixel of the array detector to this time tagging module. And then during the measurement, while you are localizing the molecules, you can also measure at the same time the fluorescence lifetime. Here you see an example. So you have the histograms of the arrival times, the micro times, for all the channels. So in this case, we had 25 channels, so it means 25 histograms. And of course, the pixels that are closer to the center of the detector, they will observe more photons, so they will have a better signal-to-noise ratio. For example, here you see in black the histogram for the central pixel, which has the most photons and therefore the best signal-to-noise ratio. And when we fit an exponential curve through this data set, we get about 2.5 nanoseconds of fluorescence lifetime. So this is just to show that you can combine the localization with, at the same time, measuring the fluorescence lifetime. So to conclude, this single photon array detector, like a spot array detector, gives you extra spatial information. And the spatial information gives you an improved localization precision already within the TCP, but especially also outside of the TCP. So you have a large field of view, and wherever the detector is within the field of, wherever the molecule is within the field of view of the detector, you can localize it with very good precision. Then it allows for multiplexing, so for measuring the position of 2 or 3 fluorophores at the same time. And it is compatible with photon time tagging, so you can use it for measuring the fluorescence lifetime. And this is, for example, very interesting in case you have a sample with multiple fluorophores that emit in the same spectral range, so you cannot spectrally separate them from each other. But if they have a different lifetime, you can use the lifetime information to separate these from each other. So what's next? Of course, today I mainly showed simulation data of ISM-FLUX and only experimental data of a specific type of ISM-FLUX. I want to combine the ISM reconstruction and the localization into a single step, so the maximum likelihood approach, and see if that performs better. And then, of course, we're also very interested in building the other ISM-FLUX configurations and do experiments with those to see how they work in practice. And then another important aspect is the background. Like I said before, in this paint sample, you have a lot of background, but this background is not dark counts from the detector, but it's mainly from fluorescence, from out of focus fluorescence. And that's because we're using an ISM setup, so a confocal setup in a certain way. And so you block out of focus fluorescence, but not as good as you would with, for example, turf illumination. So there is still a lot of fluorescence, a lot of signal from out of focus planes. But when you look at the micro image, you can separate the two from each other, because the in-focus signal has a different signature on the detector compared to the background, because what is in focus will be distributed with a more narrow distribution on the detector than what is out of focus. So with by studying, by observing the pattern on the detector, by observing this micro image, you can separate the signal from the background. And this has already been done for conventional imaging, where you have a good signal to noise ratio. But we want to apply the same technique to our DNA paint sample to see how well that works, because that would be really nice to filter out the background signal, which of course will improve the localization precision further. Okay, with that, I would like to thank everyone in my group, in the molecular microscopy and spectroscopy group, in particular my supervisor, Dr. Giuseppe Vici-Domini, the people from Genoa Instruments, which is a spin-off company from IIT, which sell spot array detectors, our colleagues from the nanoscopy group, and the people from Politecnico of Milan, and also our funding agencies, in particular the ERC and the Marie Curie Fellowship. And I want to thank you, of course, for listening, and I'm happy to take questions. Thank you.